Okay, so in some of the upcoming episodes of this series, I'm going to be identifying what I believe to be the pickups used by Eddie Van Halen at certain times and in certain places on his guitar, and for what purpose he had them, and what made them the pickups they are. Now, to understand any of this, first, of course, you're going to want to understand the difference between a humbucking pickup and a non-humbucking pickup. So make sure you go and watch that humbucking video first, and the one before it, which talked about pickups and hum, and why you hear hum with a pickup. But once you've done that, there's still a lot to know about pickups as it relates to two things. One is output. Obviously, people talk about hotter pickups, meaning it drives the amp harder, creates more distortion or overdrives the amp, more clipping. That's one thing, higher output. The other is the tone that the pickup has, or that it imparts to the sound of the strings. So I'll talk about output just first of all, or hotness, or whatever you want to call it. It's a very small topic. Basically, if you want your pickup to drive your amplifier harder, there's two things you can do. You can use a stronger magnet, or you can use more turns of wire on the bobbins of your pickup. Now, I say more turns because often people will say, well, a higher DCR, a higher DC resistance. That's usually the figure you see posted with pickups, has so many K ohms of resistance. And people will say, well, it's only got 7 K ohms. It's not very hot. It's a clean pickup. And another pickup might say it has 14 K ohms, and someone might say, oh, that's a hot pickup. And the thinking is hot means high output, but that's not true per se. DC resistance is just an indicator of two things, really. The gauge of the wire being used on the coil, because narrower gauges, thinner wire, say 44 AWG, has a higher resistance per foot than does thicker wire like 42 AWG. So 42 AWG would be the gauge used in, say, an old PAF, and a 44 would be something used in one of the hotter pickups that you buy today, or 43. Usually those are the three gauges. 44 being the thinnest of the usual ones, and therefore the highest resistance per foot. 43, less resistance. 42, less resistance again per foot. Now, output isn't a function of resistance per se. Output depends upon two main things. One, the strength of the magnet that's in the pickup, because if you've got a stronger magnetic field, more current will be developed when a string moves through that field. The second component is how many turns of wire, not how long the wire is, not how much resistance there is per foot, but how many turns of wire there are on the bobbin or bobbins of the pickup. More turns, more voltage, meaning more output. Just like more magnetism, more stronger magnet, more output, more voltage. Those are the two main things. So you might say, well, why do people always say that DCR, higher DCR, makes the pickup hot? Well, it's not that the DCR makes it hot. The DCR is not what affects the output. It's what tells you about something that does change the output. So if you've got a pickup with a higher DCR, that probably means there's more wire on there, and that probably means that there are more turns of wire on the bobbin. It's the number of turns. As the number of turns increases, the output increases. It's not what's the resistance of the wire per foot. It's not how much wire is on there per se. It's how many turns of wire. If there was a great big bobbin with one turn on it, it wouldn't be creating a lot of voltage. But if you take a length of wire and you wrap it around a bobbin many times, it will have a higher voltage, a higher output, drive the amp harder than a pickup with fewer turns. So for two pickups with the same gauge of wire making up the coil, the pickup that has more turns will be hotter than the pickup that has fewer turns. Now here's the neat thing. Because wire that is thinner has a higher resistance, it's possible to have a situation where you have a higher resistance than another pickup, and yet the outputs are the same, because the number of turns of wire is the same. So here, for example, is a graph showing 3 different bobbins, each having 5,000 turns of wire on the bobbin, but the 3 bobbins have different gauges of wire. So one bobbin has 42, one has 43, and one has 44 AWG wire. And so as the wire gets thinner, from 42 to 43 to 44, the DCR is increasing. You can see it goes from 1.737 k ohms for the 42 gauge to 2.19 k ohms for the 43 gauge to 2.762 k ohms for the 44 gauge. And yet, the number of turns is exactly the same, so each of these 3 bobbins will have the same output. So let's think about this the other way around. What if we kept the DCR the exact same for all 3 bobbins? Well, for the 44 gauge, we would need fewer turns to achieve the same DCR because 44 gauge wire is thinner and has a higher per foot DCR. We need more turns for 43 gauge because its, per foot DCR is less than the 44. And then again for the 42, it has a lower per foot DCR, so you need more turns again. But in each case, the DCR, the total DCR of the 3 bobbins would be the same, 1.737 k ohms. But even though those resistances are exactly the same, because there are more turns on the 42 than there are on the 44, the output for the 42 gauge is higher than the 43, and it's higher on the 43 than it is for the 44. And that again is because there's more turns of 42 than of 43, and there's more turns of 43 than of 44. Output depends not on resistance, but on turns. So you see the trick there. You could have higher DC resistance because you're using 44 gauge instead of 42 gauge, but if you have 5,000 turns on both pickups, on the bobbins of both pickups, they're going to have the same output approximately, because it's the number of turns, not the resistance per se. The resistance is just telling you, boy, if it has a 14 k ohms resistance, I'll bet there's a lot of turns on there, and a lot of turns means higher output. Now, DCR can affect tone, but it's not affecting tone the same way that other factors do. And those other factors are more central to tone, so we're going to talk about those ones first. I'll come back to DCR after I discuss 2 things, inductance and capacitance. But let's go through some preliminaries first. Even when you pluck only one note on your guitar, you're not hearing just one frequency. You're hearing a whole bouquet of frequencies. That's why if you hold down your low E string at the 24th fret, it will sound different than your open high E string. Every guitar pickup has what is called a resonant peak, which is the frequency that it amplifies more than any other in the spectrum of frequencies that are coming off of your guitar strings. So if you have a pickup that has a resonant peak of 4,000 hertz, and if there are, let's say, 3 different frequencies coming off your string, that's simplifying things, but let's just say there was 2,000 hertz, 4,000 hertz, and 6,000 hertz vibrating off of your string. Well, that pickup, because its resonant peak is at 4,000, is going to capture or have as its output a louder sound for the 4,000 hertz than for the 2,000 or the 6,000. You can imagine it being kind of a bell-shaped output, with 4,000 being the highest output and then other frequencies trailing off. Now, pickup designers can dial in a desired tone by making changes to the electrical or magnetic properties of the pickups that they're designing. The magnetic properties have to do with the type of magnets that are inserted into the pickup, or the extent to which they're charged, or the way in which they're charged. The electrical properties primarily are the inductance and the capacitance of the pickup. But before we discuss induction and capacitance, it'll be necessary that we first discuss current and what happens when you pluck a string on your electric guitar. Even before you pluck a string on your guitar, there's already a physical path, a path of physical matter between your pickup and the wires through your guitar and the output jack and out the cord to your amplifier and from your amplifier through to the speakers. There's a physical continuity of physical matter. That matter is all made up of atoms, and those atoms have electrons. Now, those electrons are all pushed up tightly against each other, like people pressed up against one another on a subway train when it's really, really full. So if you've ever been on a subway train, you'll know that if one person sort of stumbles forward, a whole bunch of people will be affected. They'll all kind of move forward a bit before they resume their position. Well, current kind of moves like that. Electrons facilitate the propagation of a wave of energy. Think of it also like a drop into some water. You'll see wavelets on the water going out, but it's not as though all the molecules of water are moving out. There's a wave that's changing the shape of the water, but it's not as though all those molecules are moving out. And that's the same with electrons. They simply facilitate a wave of energy. So it's not the case that in a circuit or down a cord or whatever, electricity moves like water through a hose. That's not what's going on. Rather, all those atoms have electrons, and those electrons are moving ever so slowly, really, and changing their configuration to translate that wave, to propagate that wave through the coil on your pickups, through the circuitry of your guitar, down the cord to your amplifier, through the amplifier and out to the speaker. Now that wave of energy is started when you pluck your string. You pluck your string, the magnetic field around your pickup is agitated. That causes a wave of energy to translate down or propagate down and through the coil of wire in your pickup, through your electronics, down the cord to your amplifier, which will then move the speaker. And the shape of that wave is really going to be like a wiggle of energy, moving back and forth. It doesn't travel in one direction. Remember, there's nothing traveling. It's not like electrons are moving down the cord. They aren't. What's happening is they're just wiggling, and they're wiggling to and fro. When your string is plucked, it doesn't only move in one direction. It jumps like this, right? It vibrates. And that's also what happens with the energy between your pickup and your speaker. It's a vibration. So the speaker doesn't just go out, it comes in and out because the string's going up and down, approaching and moving away from the magnet or the magnetic field in your pickup. So what we're doing is we're wiggling energy along a physical path, and the thing that facilitates that movement of a wave or the propagation of that wiggling wave is the electrons in all the matter between your pickup and the speaker. Now, one more thing. That wave of energy that moves from your pickup down to the amplifier and to the speaker, and ultimately moves the speaker, isn't made of just one frequency. When you pluck a string, as we were saying, there'll be a bouquet of frequencies, and they'll all combine to create a very complex shaped wave. And that shape, that wave shape, will determine ultimately the sound that you hear when the speaker from your amplifier is moved in accordance with the shape of that wave. That's what's going on. The shape of the wave is being translated through the electronics. Energy is being translated through the electronics by the electrons, and that's causing the speaker to move in accordance with all of the various frequencies coming off the string that you've plucked. Okay, so now let's get back to inductance and capacitance. Let's deal with inductance first. Now, I've said that there's a magnetic field and your string vibrates within it, and that creates current, and the current is a wave of energy that travels to the amplifier. Great. Thing is, though, that the magnetic field created by your magnets in your pickup are not the only magnetic field in your pickup. When the energy travels or propagates through the wire comprising the coil in your pickup, that movement creates a second magnetic field within the pickup. So let's call the main magnetic field, the one produced by the magnet in your pickup, the bar magnet's magnetic field. And let's call the smaller magnetic field created by current moving through the coil of your pickup, the coil's magnetic field. The coil's magnetic field effectively fights changes. It acts like it's storing up energy to take on the wave of energy that's coming as a result of the string moving in the magnets, the bar magnet's magnetic field. Now, to get a sense of what I mean, imagine trying to dance in mud. The deeper the mud, the more difficult it will be for you to dance. Now, you'll still be able to take those, coarse movements, the big movements, the low frequency movements like plodding your legs through the mud. But you're not going to be doing, a lot of high frequency little movements with your feet and toes as though you're doing some kind of Irish jig if the mud is very tall. It's going to be slowing you down. You're not going to be able to do the rapid fine movements. Well, that's the same thing with a pickup. The more turns of wire it has, it's kind of like deeper mud. It's better if it has more coils at storing energy. And that ability to store energy we call inductance. So deeper mud, higher inductance. Shallower mud, lower inductance. And that's why when you have a pickup with a greater number of turns of wire, you're going to have a darker tone because there is more pushback, stronger pushback from the coil against the signal that's being detected, if you will, by the magnet coil. That the magnet coil's magnetic field is producing and trying to propagate down toward the amp. More turns of wire, more pushback against that signal, more burying of the higher frequencies, more darkening of the tone, more muddying of the tone. In fact, the inductance of a coil increases as a square of the number of turns of copper wire. So, for example, if a coil with 8,000 turns were to have 4 henries of inductance, a coil with 12,000 turns of copper wire would have about 9 henries of inductance. So, higher inductance, greater loss of higher frequencies. Lower inductance, more of the high frequencies are allowed to pass through.
Hey, his sandbag fell off. Did you see that? Put a shoe off. I've never seen anyone without a handicap. He's happy. Look at him, he's freaking happy.
Now that said, the inductance of the coil itself is only part of the inductance, the total inductance of the pickup. There are other parts of the pickup that will contribute to the total inductance of the pickup. So to understand that, we first are going to have to look at 3 kinds of metal that may be found within your pickup. They fall into really 2 major categories, ferromagnetic and non-ferromagnetic. But the ferromagnetic metals fall into 2 subcategories, which we'll call hard and soft ferromagnetic. So the first category, the hard ferromagnetic, they're harder to magnetize and they don't demagnetize as easily. The second category, the soft ferromagnetic, they tend to be easier to magnetize but also demagnetize easily. And the third are the ones that don't magnetize appreciably at all and therefore don't demagnetize appreciably at all. Now the first category, the hard ferromagnetic metals, those are the ones used to make permanent magnets. Now typically an alloy of aluminum, nickel, and cobalt, referred to in short as alnico, is usually made into a bar or into a number of rods, which are then magnetized and form the permanent magnet that's in your pickup. So the bars of alnico, whether it's 2, 3, 4, 5, 8, that are in your Stratocaster, Telecaster, pickups, or the bars, the bar that's in your humbucker. Those are all hard ferromagnetic materials. They're harder to magnetize, but once magnetized, they stay magnetized for the most part. Over the long haul, you're long dead, your alnico 5 will still be magnetized as long as it's not abused. And these are the kinds of magnets that, for example, you could stick to a fridge. Put a picture or lotto ticket or something up on your fridge and walk away. The magnet would hold the photo there or the ticket there. The soft ferromagnetic would be more like the screws and slug pieces in a humbucker. By themselves, they don't stick to the fridge. Touch them to a hard ferromagnetic permanent magnet, and suddenly they act like a permanent magnet, but they're not. They're temporarily magnetic. So only when they're in contact with a permanent magnet do they act like magnets. And so you could have, for example, if you take a very strong permanent magnet and you attach a paper clip to it, you could attach another paper clip to the first paper clip and so on, sort of like a barrel of monkeys style of paper clips. But if you were to take the top paper clip and remove it from the permanent magnet, they'd all fall down because they do not retain their magnetism or their magnetic qualities. So for example, if you take the slug or screw out of your humbucker and you try and stick it to the fridge, it won't work. It won't stick to the fridge. Unlike the hard ferromagnetic material, the soft ferromagnetic material doesn't retain that magnetic quality. And then finally, we have the non-ferromagnetic or non-magnetic materials, which include such things as, your nickel silver base plate in a humbucker or the pickup cover on a humbucker. Those things, even if they're touching a permanent magnet, don't act like magnets at all. They don't act like permanent magnets. They don't act like temporary magnets. They're just, you can't pick them up with a magnet. So the non-ferromagnetic metals, when you add those to a pickup, they do not change the inductance. They don't add or subtract from the inductance of the pickup. But the ferromagnetic parts, the parts that will stick to a permanent magnet, like the screws or slugs of a humbucker, or like the base plate of a Telecaster, those ferromagnetic materials do add to the inductance, the total inductance of the pickup. Not as much as adding wines of copper to the coil would add to the inductance, but they do contribute significantly, perhaps something like 10 to 15%. And when those parts are used and they increase the inductance of the pickup overall, they further reduce the resonant peak or lower the resonant peak. In other words, the pickup will become slightly darker as a result of having used ferromagnetic materials in the construction of the pickup. So I'll just talk about Alnico magnets for the time being. I don't want to get into ceramic, but Alnico is aluminum, nickel, cobalt, and there are different compositions, different mixtures of those three elements. There's some other elements thrown into some of these magnets as well, but generally speaking, the weaker the magnet when fully charged, the more permeable that material is, the Alnico is. And when material is more permeable, it gives the pickup more inductance, higher inductance. Electrical fields can move through the magnet easier because it's more permeable, and that increases the inductance of the pickup when the magnet's inserted into the pickup. All right, so obviously then, if you've got a lower inductance, you're going to have a higher resonant peak. So if you have a magnet that's less permeable, which tends to be the magnets that when fully charged are more strong, just by virtue of it contributing a lower inductance to the pickup as a whole, is going to leave the pickup a little bit more bright than it otherwise would be with a pickup having a higher permeability magnet in it. So the mechanism is this: you take a magnet, whether it's an A3, an A4, A8, whatever it is, and you magnetize it. You're aligning those magnetic moments, all those mini magnets inside the steel, right? And that alignment of those magnetic moments makes the bar magnet or the rod magnet more permeable, so it better conducts magnetic flux than it otherwise would have. It's marginal. It's not huge. The contribution isn't huge. In other videos in this series, you'll see me magnetizing Alnico magnets, and you'll see that when we do the inductance measurement, the number of henries increases, maybe 0.3, 0.6, I don't remember off the top of my head, but it's some small amount. But the point is that whether we're talking weak magnets or strong, whether we're talking Alnico 3s or Alnico 8s, the magnetization process itself makes the magnet material more permeable, better able to conduct magnetic flux. That's not to say that because an A8 is stronger, then when you magnetize an A8, it conducts magnetic flux better than an A3 or something like that. No, it doesn't. But it is to say that no matter whether you're dealing with an A8 or an A3, you are, by magnetizing it, increasing the permeability of the material that's being used as the magnet. And when you increase the permeability of the magnet, you increase the inductance of the pickup as a whole. And when you increase the inductance of the pickup as a whole, you lower the resonant peak of the pickup as compared to what it would have been had you not yet magnetized the Alnico or whatever you're using as the material for your magnet. Okay, now let's talk about capacitance. We've talked about inductance. Let's talk about capacitance. Unlike inductance, which stores energy in a magnetic field, capacitance is about storing energy in an electric field. You can think of that electric field as building up between the coils lying side by side in the pickup coil. Technically, it's referred to as parasitic capacitance because technically it's one wire, so there is, a wave of energy moving through the wire. But because the wires lay on top of one another and they have a fine coating on them, non-conductive coating on them, they act like the coating acts like a dielectric in a regular capacitor. And so you've got energy on two sides of a dielectric. Effectively, effectively that's what's happening. And so we call that parasitic capacitance. And capacitance, like inductance, contributes to the resonant peak. In fact, inductance combines with capacitance to affect the resonant peak. Now, whereas inductance is kind of like the amount of mud that you're trying to dance in, capacitance is like trying to wear big, clunky, oversized boots in the mud while you're dancing. But it's not just a matter of lowering the resonant peak. The amplitude of that resonant peak will also be lower as the capacitance is raised. So it's more squashed. If you want to think of that curve as more squashed, that's a good way to think of it. So I want you to imagine that there's a resonant peak and that it's lower because the capacitance is higher. So it's at a lower frequency and it's at a lower amplitude because the capacitance is higher. Well, that means that the drop-off after the resonant peak is going to be less steep. So if you've got a pickup with a lower capacitance, the drop-off from the resonant peak is going to be, at least initially, more steep. It eventually levels off such that you lose about 12 decibels per octave. But before you hit that stage in the curve, a lower capacitance coil or lower capacitance pickup is going to drop off more steeply because the amplitude of the resonant peak is going to be higher for the lower capacitance pickup. And because the higher capacitance pickup has a lower amplitude resonant peak, the curve following the resonant peak is going to be more gradual as it approaches that minus 12 decibels per octave. Now, how much capacitance is added by adding turns of copper wire is affected by two things. One is the gauge of the wire. So if you have a thinner wire, I mean, the typical gauges are 42, that's usually the thickest, what you would find on a traditional PAF, 43, found on a hotter pickup where you want to have, 12, 14 K ohms, or even 44 gauge, which is if you need to put a lot of wire on there. But the problem is, as the wire gets thinner and the coating gets thinner, the wires are getting closer together. And that actually increases the capacitance. So smaller wires can get closer to one another than bigger wires. Think of it like logs. If you've got great big logs, there's going to be a lot of space between them. You'll be able to stick your hand in beside some of these things. But if you've got a bundle of straight sticks, those sticks are going to be closer together. You won't be able to get your hand in between the sticks. So finer wire, more capacitance, even at the same length of wire. Now, the second thing that's going to affect the amount of capacitance added to the pickup when you're adding winds of copper is how those winds are added. Machines typically wind wire onto a bobbin in a very linear, consistent manner. I mean, the wires are lined up side by side with one another in neat rows, and they don't cross over one another. They line up nicely, and then the next layer lines up nicely with that, and so on. Well, that's going to increase capacitance as compared to if the wires are kind of splayed in different directions on the coil. And usually, we will say that if a person's winding a coil by hand, so they're guiding the wire onto the bobbin as the bobbin spool is spinning, if they're doing it by hand, the wires are going to be on a bobbin in a much more scattered fashion. They aren't going to be as uniform on the bobbin. They're going to be more scattered. And that means they're not going to be as close, right? If you take a bunch of logs and you put them this way, you're not going to be able to fit them into those grooves, right? They won't fit into the grooves as nicely. They're going to be all like this, a big pile or a mess. Well, when that big pile or mess exists and they're not as close together, the capacitance drops. The turns of wire act more weakly as a capacitor. So the parasitic capacitance is decreased. And that's why some people will spend big money paying pickup winders to provide them with hand-wound pickups. They want that scatter winding so that they don't lose as much of the high end. Now I'll just add one other thing with respect to capacitance and inductance. You remember how I was saying that adding ferromagnetic parts to a pickup increases the pickup's overall inductance and lowers its resonant peak? Well, that's true. Those screws and those slugs in your humbucker being ferromagnetic, do lower the inductance. But unlike adding wires of copper to your coil, adding ferromagnetic material to the pickup does not increase the capacitance. All right, so we've talked about inductance, we've talked about capacitance. We now know that there's this resonant peak, and that's the peak frequency, the frequency that's loudest among all the frequencies being picked up by your pickup, determined largely by the inductance of the pickup, which is the number of turns, and the capacitance of the pickup, which is determined by things such as, how your wires are laid out and the gauge of the wire. Now, let's talk about DCR, though, in relation to that curve. With respect to DCR, changing the DCR does not change the resonant peak. What it does do is affect what they call the Q value. So with a lower resistance pickup, the peak will be both higher and more tight and spiky than it would be if the pickup had a higher resistance. In other words, for the same inductance and same capacitance, more resistance means flatter peak, not a change in where it resides. It's still the same frequency, the same peak frequency, but it's more like this instead of like that in terms of its sound. And so higher DCR is going to give you a more rounded out or balanced sound, less spiky. You might think of it as warmer. And that's not to say that DCR increases the volume. Remember, we talked about that at the beginning. It's the number of turns that affects the output, and that number of turns strongly affects that resonant peak where it sits. But the DCR does affect the shape of that curve. So for example, if we've got an inductance of 3 henries and a capacitance of 500 picofarads, and we use 3 different gauges of wire, let's say one that causes a DCR of 3K ohms, one that causes a DCR of 6K ohms, and one that causes a DCR of 12K ohms. Well, you can see that those 3 different kinds of wire are going to have an effect on the height of the resonant peak. So let me just close in a little bit closer here and I'll just show you. And so the 3K ohm pickup, the pickup with the resistance, the wire giving it a resistance of 3K ohms, has an output of 28.2 decibels. When we move to the 6K ohm pickup, it has 22.2 decibels, and when we go to the 12K ohm pickup, it drops down to 16.2 decibels. So as it drops down, the curve is, in a sense, getting less spiky, right? Because the beginning points and the end points are the same. It's just that the middle is dropping down, and that's making it smoother. Okay, next let's talk about magnets, the magnets that are in your guitar pickup. Here's a bar magnet. It would get magnetized along this edge and this edge in basically usually a vise is what I would use, with big strong N52 neodymium magnets on each jaw of a vise, and you move the 2 jaws in like this so that they touch the 2 edges like that. And when you move the vise jaws apart, you've got a magnetized piece of metal. Most of the guitar pickups will use a combination of aluminum, nickel, and cobalt, with a few other trace materials in there, referred to as alnico or alnico. And there are different grades of magnet that differ in terms of, well, 3 things. One is permeability. Permeability is the ability of a bar, of metal, the ability of it to allow magnetic flux, fields of magnetic flux to flow through it, okay? And the higher the permeability of the bar, the greater the inductance of the pickup as a whole will be made. Not a lot, but it does contribute to the inductance. And so what you'll normally find is that the weaker magnets are the more permeable magnets, and that therefore they allow the inductance to rise more. So when the inductance rises more, the resonant peak frequency decreases, and that means you get a slightly warmer sound. So you might say, oh, is that why an Alnico 2, which is sort of a weaker magnet, is said to be warmer than, say, an Alnico 8, which is said to be more trebly or spiky? That's a small part of it. An Alnico 8 isn't as permeable as like an Alnico 2 or an Alnico 3. So permeability is one thing. If we have higher permeability, we have a contribution toward the inductance, and that lowers the resonant peak, making your guitar sound a little bit warmer, a little less spiky, a little less trebly. Okay, permeability. Leaving permeability aside, there's two main properties of a magnet that we talk about. One is coercivity. So if I put this in a magnetizing rig and I magnetize it, then depending on what kind of metal this is, Alnico 3, 2, 4, 5, 8, it will have a greater or lesser ability to demagnetize later on. So when they were developing these various Alnico alloys, they were trying to create an alloy that would not lose its magnetization as easily. And ultimately, you know, these stronger magnets, you know, the Alnico 8s were developed later than, say, the Alnico 2s and 3s. And so they had a better ability to hold on to their charge once they had it. They had a higher coercivity. Well, the magnetic field runs from end to end, okay? And when they're closer in, the lines of the magnetic field are close to the bar. And as you get further out, they arc more broadly and they get further apart. So the ones that are close to the magnet are tighter together, more pinched together and smaller. And as you get further out from the magnet, the lines are more broadly separated and larger, okay? Well, let's deal first with the high coercivity. So we've got, let's say, an Alnico 8. And what that means is if I were to measure where the magnet is strongest, well, it would be right here on the top edge, okay? Right on the edge. But if the coercivity is lower, what happens is that there's a recess. So if there's a lower coercivity factor for the magnet, its most strong point won't be at the edge. It'll be a little bit in, maybe a millimeter, maybe 2 millimeters. Okay, and so lower coercivity moves the effectively strongest part of the magnetic field into the bar, and therefore further away from your strings. Now, the other thing about these magnets, we've talked about coercivity. There's also what's called remanence, and you can think of that as like the strength of the magnet. So when you put magnet into a magnetization rig, like I just talked about, between two other magnets, and then pull it apart, it's not quite as magnetic as it was while it was still in the rig, but some of the magnetism remains. There's remanence. So the magnet is now a permanent magnet. It's not as strong as it was when it was touching the N52 magnet that was used to charge it, but it has remained to a certain extent magnetized. The different magnets can be magnetized to a different extent. Generally speaking, they increase in strength when you go from Alnico 3 to Alnico 2, which is stronger than Alnico 3. Alnico 4 is stronger than Alnico 2. Alnico 5 is stronger than Alnico 4. And Alnico 8 is stronger than Alnico 5. All right, stronger meaning stronger magnetic pull, okay? So an Alnico 3 can maybe be magnetized to about 650 Gauss, thereabouts. Whereas an Alnico 8, the strongest magnet, can maybe go to 1,000 or 1,200 Gauss, both when fully charged, okay? A magnet that is stronger will have a more dense and tight magnetic field. If the magnet has a lower Gauss, it will have a more broadened out magnetic field. Now, people generally say that the Alnico 2s, the Alnico 3s, they tend to be warmer or muddier sounding than, say, an Alnico 8, which is said to be more spiky with enhanced, high end, enhanced low end, and a scooped mid, less of the mid frequencies being heard. And that can be a bit harsh for some people, especially if it's put in the bridge position. So what's happening with these stronger magnets with the narrow, shorter magnetic field? Well, imagine that you're trying to capture the frequencies moving along a string, okay? Generally speaking, for a complete wave of the string, one complete cycle, you need a longer length of string for a low frequency than you do for a high frequency. Higher frequencies don't take that much string. They, if you've got a really high frequency, maybe it only takes a millimeter of length or less I'm just going to pick a number at random, okay? Let's pick a number at random. Let's say that for a certain frequency, a high frequency, the whole movement of the string for that frequency takes about 1 millimeter. And let's say that for low frequency, it takes 10 millimeters, okay? That much, let's say. And let's say that for a mid frequency, it takes about half, like midway between the high and the low. It takes about maybe 5 millimeters. Well, obviously, if you've got a bar magnet that's got a high coercivity so that its strongest point is right at the bar magnet, and if that bar magnet is closest as it can get to the strings, then the strings are going to be exposed to a very small magnetic field. That's the part of the magnetic field, the one that's tight and close into the magnet. That's the part that's going to be exposed to the strings, or the strings will be exposed to it. And therefore, that small, narrow magnetic field will only see a small length of the string at its most powerful position in the magnetic field. And that's going to give you, let's say, louder high frequencies. Well, what about like the low frequencies? Like we said, that was like, 10 millimeters. Well, those things are moving the string so much that even though they're being exposed, they're traveling within a very narrow part of the magnetic field, they have such a magnitude as they can be heard anyway, right? So they really push a lot of voltage. The middle frequencies, like let's say that was 5 millimeters, they're not quite short enough to be captured within the first ring of that magnetic field, but they're not big enough to make up for the fact that they're not small enough, like lower frequencies are. And so you end up with boosted up high frequencies, boosted up low frequencies, and not boosted up mid frequencies. People will call that scooped mids, but really what it is if you had a level distribution of frequencies, and then you took the ends and you moved them up, that's what's really happening. And so an Alnico 8 not only has higher coercivity, and therefore, the magnetic lines are right up close to its poles, but also the remanence of an Alnico 8 is stronger, so it's got a greater pull. Tighter lines right at the surface, and therefore tighter lines as you go out and out and out from the magnet. So again, narrower, picking up less of the string, emphasizing the brights and the very strong low ends, while the mids don't get any help, don't get any love. But this is the interesting thing. You might say, well, an Alnico 8 is composed of an alloy that is such that it creates a spiky field. Yes, but only because an alloy like an Alnico 8 can be charged to a higher Gauss rating than an alloy like a Alnico 2 or an Alnico 3. And it's the Gauss reading. The higher the Gauss reading, the narrower that field and the shorter that field. The lower the Gauss reading, the broader that magnetic field, and the further it will extend. Now, this is the important thing to understand about this. It's not the case that a weaker magnet, because it's weaker, has a higher inductance. It's not related to inductance. So imagine you took an Alnico 3 and you charged it fully, and let's say it was at 650 Gauss. And then you took an Alnico 8, which could be charged up to, say, 1100 Gauss or so. But instead of doing that, you didn't charge it fully. You only let it charge to the same Gauss reading, 650. So you've got an Alnico 3 and you've got an Alnico 8, and they're both reading right across their length 650 Gauss. In that situation, the Alnico 8 will sound brighter than the Alnico 3, even at the same Gauss reading, not because of the shape of the magnetic field. The magnetic shape of the two magnets will be exactly the same. It's the 650 Gauss that's determining the shape, right? So why does the Alnico 8 sound brighter? It's a less permeable metal, less permeable alloy, therefore it has a lower inductance, and because it has a lower inductance, it has a higher resonant peak. So you could take an Alnico 8, charge it only partially so that it had a broad, tall magnetic field, just like an A3 or an A2. But it would be brighter than an A3 or an A2 because it's less permeable than an A2 or an A3. So there's two things going on with magnets. There is the strength of the magnetic field, which determines the shape, which makes it more spiky. If it's stronger, it makes it more broad. If it's weaker, but then there's also the materials of which the magnet is made. The more permeable the magnet is, the higher the inductance is going to be, the lower the resonant peak. So finally, of course, there's the position. We mentioned that already, but I'll just mention it independently. If you move your magnet away from the strings, you're exposing the strings to a broader part of the magnetic field. I should turn it this way, but you know what I'm talking about. The magnet is magnetized from here to here. So the magnetic field goes like this and it goes like that. And if we move the magnet further away from the strings, instead of getting the tight little, turns that are right here of the magnetic field, we're getting the broader ones exposed to the strings. And that's why you can warm up even an Alnico 8 by descending it into the guitar pickup cavity further. What you're doing is exposing the strings to the broader lines of the magnetic field. That's what you're doing. And because those lines are broader, you're picking up more of the string, and therefore you're getting a greater range of frequencies off the string. So let's have a look at a couple charts or graphs that'll show you what I mean. First, we'll look at just a graph showing magnetic fields and how, as you get further from the magnet, the fields are getting broader and also weaker. Okay, they're getting further apart. Now let's imagine that you take a magnetic field, therefore, like that, and you put it, let's superimpose it with a side view of a guitar's pickup and the strings, okay? First, let's look at it in a situation where we move the graph of the magnetic field lines close to the strings, and you'll see that the part of the magnetic field that's being exposed to the string now is a narrower part, a shorter, narrower part. If we move the magnet down, in other words, superimpose the graph at a lower level, deeper into the guitar, further away from the strings, look now, you can see that it's the broader lines of the magnetic field that are interacting with the strings. All right, so with respect to tone, we've talked about the effects of, inductance, capacitance, resistance, the magnet, the Gauss of the magnet. There's one other not insignificant thing that contributes to the sound of the pickup, and that's in two major ways. And what I'm talking about is the geometry or the shape of the coil. So you'll know that, for example, if you look at a Telecaster coil, it's a really tall pickup, right? As compared to, say, a PAF or any other kind of humbucker, or especially as compared to something like a P90. P90 is about the height of a short cookie, and a Telecaster is probably 3 times the height of that. So in the bridge position. So the point here is that if the pickup has a coil, let's just deal with single coils for the sake of ease just for a minute. If it has a coil that is taller but narrower, then the magnetic field that's around it will not interact with as much of the coil as it would if the coil were shorter and wider. So if like for example, in a P90, you've got a coil that's short and wide, so the magnetic field is interacting with more coil than it otherwise would if the coil were narrower, and here the magnetic field's out here, not interacting with coil, right? But if the coil's out here where the magnetic field is, more of the magnetic field, more of that flux is interacting with the coil. When that happens, the inductance of the pickup increases, and it's significant. It's not just like half a Henry, it's several Henrys difference between, for example, on the one hand, a Stratocaster pickup, and on the other hand, P90. Stratocasters, or the Telecaster, is very narrow and tall. P90 is very squat and wide. And so it has a much higher inductance. And you'll recall from what we said earlier on, higher inductance means lower resonant peak, a bit warmer, not as spiky. Okay? So that's one thing. The geometry affects how much it interacts with the magnetic field. But the shape of the coil also affects how it interacts with the strings. Now, here's what I mean. So let's just deal with, for example, first of all, a Stratocaster pickup. So a Stratocaster pickup is narrow and relatively tall, and it sits under the string, and the amount of string it sits under is fairly narrow, okay? So that means that when higher frequencies, when the strings are moving at higher frequencies, a narrow pickup will pick up those frequencies, but it will not pick up as easily or as well the mid frequencies. So this is exactly the same as what I talked about before, except for this is a different consideration. You'll recall I showed you the video of the wiggling strings, right? But that had to do not with the shape of the pickup coil, but with the shape of the magnetic field, right? So the coil itself has properties, its spatial properties are such that when it's narrower, it's under a smaller length of string. And as such, it has similar properties to what we were talking about before, where the high end is kept intact, the low end is so strong a wave that even though a small area of the string is being seen by the pickup, the wave has such a big motion that it gets picked up by the pickup anyway. And then we get that scooping of the mids because the mids are, the wavelengths are too long, and they're also not big enough to make up for the fact that they're not short enough to be picked up as well as the high frequencies. So what happens when you replace something that's a narrow tall pickup with a broad short pickup? Forget about short for the moment. Just think about broader. That coil is now under a longer length of the string. So P90 might be under this much, and a Stratocaster might be under that much, right? The P90 being broader, think of all those turns of wire on the coil. Think of each one of them, every turn, as its own pickup, okay? So when that wave is moving along any given string, each of those turns of copper on the coil, each of them is picking up the string, let's say the piece of string that's immediately over top of them. So on the outside of the coil, you know, it's capturing the wave when it's up here, let's say, and a little further in on the coil, it's capturing the wave when maybe it's here, and a little further in on the coil, maybe it's capturing the wave when it's right here. So because they're spatially arranged, because those wires are not all sitting exactly in the same spot, but they are spatially arranged, the wave, when it's being picked up by this guy, is only here, and then we see that by over here, this guy's seeing the wave when it's up like that, up higher, okay? So it's as if all of those strings were individual pickups, but we sum the signals that they're receiving. They're all different signals. This guy's receiving the lower amplitude, this guy's receiving the higher amplitude, this guy's receiving the negative part of the wave because it goes up and down over the zero line, right? And this guy's receiving maybe the positive part of the wave, and we take all those values and we sum them up, and we're going to see something that's a mishmash of the various amplitudes of the same wave. Because high frequencies have more cycles per inch than mid frequencies, and those have more cycles per inch than low frequencies, there are more cycles per inch for those turns, which we're calling pickups, but they're not pickups, but you know what I'm saying, pretend they're pickups. There are more cycles per inch, and therefore there's more averaging going on for the higher frequencies than there are for the mid or for the low. So when you have a coil that's narrower, let's say like this, these guys here, each being like a pickup, are picking up closer area of the string, right? But when you replace that pickup with a P90, now all these little pickups are picking up much more varied amplitudes of that wave. So the broader the pickup gets, the more those various amplitude readings, if you want to call it that, are summed, and to some extent are canceled out. So we can call this smearing, if you like. The broader the pickup coil, the coil itself, the broader the coil, the greater the amount of smearing, especially on the higher frequencies, less so on the mid frequencies, and not even really significant on the low frequencies. So that spatial separation being wider, you know, the coil being wider, is capturing a longer length of the high frequencies, and therefore they're fighting one another within the coil and canceling out some of those high frequencies relative to how it's being done for the mids and the lows. And that means that those highs are being brought down from where they would be if we had a Stratocaster in there instead of a P90, okay? Now, there's one other thing to consider. What about when you have two coils, right? You've got, in a humbucker, a coil here and a coil here. Now we can see that, yes, they're spatially separated, and to that extent, they're going to do the exact same thing as the P90 will. They're reading different parts of the string at the exact same time, and those signals are going to sum. But in addition, to compound it, the two coils of a humbucker are wired in opposition. So they actually, the one coil fights with the other coil, further taking away some of the high end. So that's why you've got a Stratocaster is more spiky and clear, and the P90 brings that down a bit, it's more mid-rangey, and then the humbucker even deeper than that. So the skinny tall one, spiky because it captures a small amount of the high frequencies, a small spatial length of the high frequencies on the high strings. The wider single coil, like the P90, captures a broader area, and that causes the smearing of those higher frequencies and a leveling out of the frequency band so that you can hear more of the mid-range. And then finally, in the humbucker, we do have that smearing, plus we've got the two coils fighting one another. The wave in one coil is not quite in phase with the wave in the other coil, and so they're canceling out to some extent, more so on the high end than on the mids and on the lows. So we've got two functions going on here. A broader coil gives you a pickup with higher inductance because it has more interaction with the magnet, with the magnetic field, and a broader coil will end up smearing over those varying, slightly different phased parts of the detection of the high frequency wave. And even worse when you have two coils doing it. All right, that might seem a bit abstract. I hope it nonetheless was understandable, and I think we can go and sum up now. So I think the best way to summarize all of this is there are so many moving parts, so many moving pieces in the puzzle, so many parts of the stew in a pickup that I couldn't sit here and summarize, well, it's simple, just do this, this, and this, and you get that kind, do that, that, and that, and you get the other kind. Obviously, you can mix and match all of these ingredients. You can remember that adding capacitance will lower the resonant peak and will also smooth it. You can know that more turns of wire is going to increase the inductance, or that having a broader coil is going to increase the inductance, and doing so is going to lower the resonant peak. You can know that adding more resistance is going to bring down that peak, that resonant peak, and sort of smooth out the curve of frequencies. At the same time, you can look at the magnetic properties. You can say, if I have a magnet that's more permeable, it's going to add to the inductance. If I have a magnet that's less permeable, it's not going to do so as much. And it tends to be the case that the magnets that are stronger, the A5s and the A8s, aren't as permeable as the ones that are weaker or darker. In other words, they can't hold as much of a Gauss, they can't be charged to as high a Gauss as the A5s and the A8s. You can know that the Gauss itself is going to have an effect on the shape of the magnetic field interacting with the string, such that if it's a highly magnetized bar or magnet, the magnetic field is going to be tighter and shorter and narrower, and it's going to, pick up more of the highs, amplify more of the highs, amplify more of the lows, and not do any favors for the mids. And we could go on and on, but I don't want to revisit the entire video. It's been a long one already. Now, finally, I'm not saying to you that Eddie Van Halen, knew all of these things that I just talked about in this video. But I don't doubt that he experimented with magnets and coils and the shapes of coils, using P90 maybe, or a Stratocaster pickup. Or at one point, I remember he said he'd used two Stratocaster pickups. He wound them together like a humbucker. He fiddled with pickups, so he would have known just through experience that if he uses this A5 instead of an A2, he's going to have a higher output pickup that's going to be brighter than the A2 was. He would know that, oh, this pickup's got a lot of turns on it as compared to this one, so it's got a higher DCR, he probably would know that. But that in particular is going to sound darker, right? He wouldn't have to even know what inductance was to know that it sounds darker if it's a pickup with a lot more turns on it, and so on and so forth. So I have no doubt at all that Eddie was quite expert at knowing through experience, a pickup like that's going to sound dark. Oh, a pickup like that's going to sound bright. Hey, if we take this out and stick that in, it's going to brighten it up. Hey, if we take this out and stick that in, it's going to darken it up. Does anyone really doubt that he had experience doing that? I don't have any. And so all I've really done in this video is tried to explain the whys and the wherefores of darkening things up, increasing or decreasing the output, brightening things up, in ways that you can predict without having to spend as many practical hours fiddling or years as Eddie Van Halen clearly must have working on his guitars. You can pretty much dial it in. You can say, sounding a bit dull, want to brighten it up. I think I'm going to try an A8, or I'm going to try a coil with fewer turns, or what have you. So hopefully you've learned a lot in this video, and hopefully it will help you to understand what's coming. Now in the next video, we're going to look at an iconic piece of Eddie Van Halen virtuosity, and we're going to look at how Eddie might have picked the pickup that he used to maximize the sweetness of the sound he was making. See you then.